Thank you for introducing me, Joe. Okay. All right. Thank you for everyone coming to Spark Summit today. Today, I would like to share some exciting work we have done so far inside Two Sigma. It is a distributed time series analysis framework for Spark named Huohua. Huohua is the Chinese pronunciation for Spark. So something about me. So my name is Wenbo Zhao. I'm working at Two Sigma Investment based on New York. Two Sigma is an investment management firm. It is also a cutting-edge technology company which applies math, computer science, and engineering in the fields of finance and investment. So this talk is about time series. So what is a time series? So in Two Sigma, we view every data set as a time series data. So for example, the stock market prices, the temperatures over different time, the sensor logs, and the presidential polls. So, but really, what is a time series? In theory, a time series is a sequence of observation obtained over different time order. So, for example, the corn prices over different time stamp is a time series. Stock prices we observe from the stock market is a time series. So what do we do for time series like this? We are an investment management firm. So what we are trying to do, we try to forecast the time series data set for the future value based on the previous historical data sets. So for example, we want to know what's the corn prices in the next day, what's the stock prices in the next minutes, so that we can if we can make this forecast in an accurate way, then we can invest we can make smart invest decision for us and for our clients. But sometimes if we want to do a better forecast, we may just use one single time series data. For example, we may need to use multiple time series data sets. For example, for this particular example, for the corn prices, if we want to forecast the corn prices in the future, in the next day, if we only use the corn prices and its historical data itself, we probably won't be able to make a very good forecast. But if we can join this temperature data set with the corn prices together, then probably we can make a better model to forecast the corn prices we are interested in. So now that the temperature data set has unaligned time step to the corn prices. So in order to this kind of join, we need to perform so-called temporal join to join different time series from different data sources. And Huohua enables the fast distributed temporal join for large-scale time series data sets with unaligned timestamp. Okay, so what is a temporal join? A temporal join is a particular join function defined by a matching criteria over time. So just like the join in this relation database, we have left join, right join, inner join, symmetric join, all kinds of different join. But what makes temporal join so special? Because it's join criteria. For example, we have this example of join criteria. We want to look backward. We have two time series here. One, we want to do a left join from the left to the right. And then the look backward criteria basically saying if we cannot find observation from the right-hand side, then we fall back to the historical data, the previous historical one. So we'll try to find the most recent observation from the right-hand side to match to the left. So similarly, the look forward criteria basically saying if we can't find a match from the right-hand side, then we look into the future and find one which is close to the left-hand side. That makes sense? Okay. So here is a small example to show how temporal join work with the look backward criteria. So we have two time series here. One is the weather, the other one is the corn prices. For the weather one, notice that we sample the data every 2 hours. And then the corn prices, we sample the data every three hours. So these two time series has unaligned timestamps. So we are doing left join, so we have 3 rows, and this is the table looks like after join. And then for the 8 a.m. Data, then we can match them together as usual. But if we consider the 10 a.m. one, then because in the comprises, we don't have the 10 a.m. rows in the comprises one, so we fall back. We look back to the history and find the closest one, which is the 8 a.m. one, which is like $2. Similarly, we have the join for the 12 a.m. one. We fall back the price at 11 a.m. Okay, so in practice, we have thousands of such market data sets. We are interested. We try to forecast, like the stock price, the equity price, the option price. We want to forecast what's their value in the next 2 days, in the next 1 second, or even more granularity. And we have hundreds of thousands of data sets with unaligned timestamp. This like the weather, the presidential polls, and all the other random events, the tweets, all different kinds of data. And this kind of data is like, there are so many that if we can find some of the combination between these two and join them together and study together, then probably we'll make a better model, a better forecast to those market data sets we are interested in, we want to forecast. And then we can make a better trading strategy upon of it. So we need a fast and scalable distributed temporal join for this kind of data sets. Okay, so what's the existing issues what's the issues with the existing solution? For now, a single time series may not even fit into a single machine, or may not even fit into a small cluster. So we have like some time series like could be like 300 terabytes of data, which cannot even fit into a small like cluster. And then like what we said, so when we do forecasting, we may not just use 1 or 2 time series. We may use like hundreds of time series coming from different resources. And then the existing package so far couldn't support the temporal join, the simple temporal join, as I mentioned, we want, and cannot handle this large-scale time series, like MATLAB, Panda, all this kind of single machine, single library. And then even for the Spark-based solution, we cannot, the Spark-based solution for short, like we cannot, for the pair RDD functions, we try the data frame data set. This kind of, and Spark TS, this kind of library cannot even support the temporal join, this kind of functionality we want. But Spark is great. Spark is so reliable, so fast. We want to use Spark in a more smart way. Okay, so that's why we developed Huohua, a new time series library for Spark. And at the very beginning, when we developed Huohua, we try to solve the temporal join problems, but we found out Huohua is not just be able to solve the temporal join problem we want. The Huohua can also use for all the general purpose of time series analysis. So we scale up Huohua a little bit up. So we want to use Huohua to provide a collection of functions to manipulate and analyze time series data at a large scale. And then like the group functions, temporal join functions, we want to support this kind of commonly used time series analysis functions on top in Huohua. How do we achieve such goal? So what we do is the first thing we try to do is we try to build a time series aware data structure. This is we extend the normal RDD from Spark to time series RDD. Using this time series RDD, we can perform a lot of optimization for the functions using this time series RDD by using the temporal locality. And then by using the temporal locality, we can reduce the shuffling, and we can reduce the memory pressure by streaming. When I say streaming, this is not the Spark streaming. I will explain what streaming means in the later slides. So, what is a time series RDD in Huohua? So a time series RDD extends RDD to present the time series data. So what makes the time series RDD so different from the normal RDD in Spark is that we associate a time range to each partition for the RDD. So and then when we do different kinds of operations on top of time series RDD, we track the time range for each partitions. And then most important things, after all the operations on top of time series RDD, we preserve the temporal order of the data set. Okay, so if we think the time series as a domain and functions on top of this time series domain, then time series RDD basically represents time series data, time series data set, and then operations on top of time series RDD present the functions in the time series domain. Okay, so here is a very small example to show how do we use the time series RDD to present time series data. So we have this time series data for two columns. One's the time, one's the temperatures, and we have 3 hours data and 6 a.m. data, 7 a.m. data, and 8 a.m. data. Each hour's data are labeled with different color. So in the normal RDD, we probably will use one partition to present the first hour's data, and then we use maybe another partition to present second hours of data, and so on. But for the time series RDD, we associate a range for this for each partition. For example, for the first partition, we'll say the range is from 6 a.m. to 7 a.m. and basically they're saying all the rows in the first partition, their timestamp are within this time range. Okay, so and so on, and for the last one, basically saying the data are within 8 a.m. to the infinity future. So okay, as an example to show how to use time series RDD to do all kinds of operations we want for time series analysis. So first thing I want to do is I want to show how to use time series RDD to do a very simple operations, the group function we want to do for time series data sets, as a small example to warm up and show the benefit of using time series RDD for this kind of analysis. So a group function is to group rows with similar timestamp. So an example of group function is to group rows with exact same timestamps. So for example, we have this time series data for the temperature, and then for the first two rows are the temperature from New York and San Francisco, and then they are sharing the same timestamp. So by this group function, we'll group them for the first. We'll group them together, and then and so on and so on and so on. And another kind of group example for group function is that we try to group rows with nearby timestamp. So for example, we want to group rows within every 1 hour. So we probably will group the first 4 rows as a single group, and so on. The last 4 rows as another group. So in time series analysis, we normally will group these different rows with different timestamps together, and then we perform further analysis for each of this group. Okay, so what do we do if we just we want to group rows with exact timestamps, and how do we do this one in Spark? So supposedly we have RDD with 2 partitions, and then the underneath data has been ordered by the timestamp, and then because we know we try to group with the exact same timestamp, then the first 2 rows will become a group, and the third and fourth row will become a second group. So we can call group by functions, and then because we are calling group by, and by the hash partitioner, we'll basically shuffle the data around. And then we shuffle these 2 here, 4 here, and so on. So after group by functions, after group by this method, then data are shuffled between different hosts or different partitions, and your data and also has been materialized in the host of the in the partition or in the worker to holding the partition. And then the most important thing is after the group by, the temporal order is not preserved. So basically, if you want to reconstruct the temporal order, then you need to call a sort by function. So you probably will do another shuffling after you calling the sort by. So to come back to the temporal order. Okay, so that makes sense. So what do we do if we want to perform similar operations in time series RDD? So in time series RDD, we know the underneath data has been ordered by their time. So we can perform these group operations per partition and locally, and also streamingly. We don't materialize data in the worker. We only on the fly to group them and use them on the fly on demand. So for this particular example, we know we can perform such because their data are, we know all the groups are coming as sequentially, so we can perform this kind of group functions one by one in as an iterative way in a streaming fashion. Okay, that makes sense. Okay, so finally, this is the benchmark we for group. So we're running, we did a group by and sort for the RDD and data frame, and also we apply the group functions on our time series RDD, and then data are stored in HDFS, and we do in a single count after the group functions to force these operations can be materialized. So comparing to the RDD pair functions, we have achieved like 50x to 100x speed up, and comparing to the data frame, we achieve like 5x to 10x speed up. Okay, so finally we reached the temporal join problems we want to solve at the very beginning. We just remind a little bit what the temporal join is. It is a function to defined by a matching criteria over time. But in practice, a particular matching criteria has two parameters. One is the direction, whether we want to look back to the history or we want to look into the future. And the other one is the windows, how much we want to look back and how much we want to look into the future. So here is a small example. So we have 3 observations in both sides. If we want to look backwards with a small window, then we probably won't be able to find a match for these 2 time series. But if the window size is a little bit longer, then we will find a match from left to the right. Okay. Okay. So suppose we have the time series data set like this. So if we have a single machine, so everyone could simply write a streaming algorithms to join these 2 time series together with a temporal join with a look back criteria and window of less 1. So for example, we can join 1 a.m. from left to the right, and from the 2 a.m. and 1 we can join like this, and 4 we will join to the 3. So basically you have an iterator from both sides and then iterate through these 2 time series and perform the join as this one. Okay, so everyone can write a very simple program to do that. But how do we do that in time series RDD setting? So we have 2 time series RDD and each have 2 partitions. How could we perform the temporal join in time series RDD in a smart way, in an efficient way? So what we're trying to do is that we partition the time space into disjoint intervals. Like this, for this particular example, we partition the time series into 2 intervals. And then for each interval, we will have a partition for the joint time series RDD. And then know that for each partition in time series RDD, we check the time range for each this time series RDD partition. So we can use this metadata to build the dependency graph from the joint, from the parents to the joint partition. So we'll know, for example, for the first partition, for the second partition, we know we need some data from the first partition from the right-hand side. That dependency graph is built by using the time range associated for the time series RDD partition. So, okay, once we build the dependency graph, we can join the data on the fly in a streaming fashion. So, for example, when we do the count, the join time series RDD, it will bring the data from left-hand side and right-hand side in the first partition, and from the left-hand side and from the right-hand side in a streaming way. So when we join the two AN from the left and the YN from the right, then the first row in the join partition will be throughout. Because we are doing streaming, so we don't materialize all the data sets in once inside the join partition. And similarly, for the 4M here, we'll join 3 from the first partition, and so on. Okay. So here is a benchmark to show our temporal join comparing to our implementation of our temporal join comparing to the RDD, data frame, and time series RDD. So as I mentioned, because RDD and data frame don't support the temporal join, so what I can do, this comparison basically just the window size is 0. So basically we are doing exactly left join for this particular example. So for comparing to the RDD, our time series RDD achieve like 20x to 50x speed up, and comparing to the data frame left join, we can achieve like 5x to 10x speed up as well. Okay. So by using similar approach for the group function and temporal join functions, we develop other kinds of functions on top of time series RDD. Like we can do the window functions, interpolarization functions, and for different kinds of temporal join, we already developed like look backward, look the future, and also the symmetric join, inner join, all different kinds of join. And also we add the summarizer functions like summarizer, like average, variance, all those kind of different summarizer, and we can apply this summarizer to the windows, intervals, and cycles, as I mentioned. So okay. So this is we are trying to. Unfortunately, we haven't been able to open source Huohua right now. We are planning to open source all the implementations of Huohua in the near future. So if anyone would like to, will be interested in working with us, please contact us. So, but please follow up this link to see any updates for Huohua. So here's some future work we want to do. We want to integrate Huohua to data frame and data set API, such that we can get like more speed up and like the cogent and more richer APIs. And also we want to provide Python bindings to Huohua for the time series RDD as well. And we want to implement more summarizers. Okay, so this is the list of key contributors to this Huohua project. I'm so happy to be here to present to the team for this work. Okay, thank you.
Guys, have any questions? I can run it around. Okay, I'll go in this ascending time series order here.
Thank you for the talk. I have a couple of questions. So when you are joining, are you actually replicating the data on both sides and create a new data? Or if not, then looks like you will have a case where data has to be existing more than one partition or more than one host. How do you resolve the situation?
So, so your question is basically saying, your question is asking whether I replicate the data.
Right.
So, So we actually not, I mean, in a sense, we are not actually replicating the data. We are reading through in a streaming way. So you are right. So if one partition need to, in the join partition, if these two partitions need to both access the same data, then they'll be sending to two copies of two different hosts. Okay. That's true. But we don't keep them in the memory, so we don't have memory pressure.
Okay, on the fly. Okay.
Yeah, we're just doing streaming.
So my second question is, when you are joining, looks like your partition time window will even, I mean, generally will get bigger.
Yes.
Because you have to get a window that is wide enough to cover both sides, right?
Yeah.
So do you repartition it after at some point, or?
Yeah, I mean, you could do repartitions for both sides at the very beginning.
Okay.
So then you can reduce the dependency, but that make too much difference basically, because when you do coerce, even though you do a smaller way, it's basically just
so basically pre-tune your time window so that it matches lattice point. Is that right?
Sorry.
You basically set the time window so that both sides matches in a certain nice way.
Yes.
Okay. Thank you.
Somebody here.
Thank you very much for the presentation. Very interesting. Question. You mentioned that your data has to be pre-ordered in order to create a time series RDD.
Yeah.
Do you simply pre-order it in Spark, or do you actually support reading from databases? For example, from the JDBC, the data is already ordered by the database.
Okay. So in let me say this way. So in financial industry, almost 99.99% of data has been logged or stored in time order. That makes sense. That's the basic assumption. So even though your data set haven't been sorted or by the time order, then you can just run a one-time job to sort it and store them together.
But so you simply assume the order of the data of the underlying data, right?
Yeah, but we assume that. But we also, I mean, if you're just using unsorted data, then you're basically just calling a sort by.
Okay.
Yeah.
And you simply cast or convert the regular RDD into time series RDD.
Yes.
And it will just automatically assume. Okay.
So we provide API to convert like the normal RDD, no matter whether it's sorted or unsorted, or a data frame to the time series RDD.
Okay. And when do you think you're gonna open source it? Within a year or half a year or?
We hopefully can open source in a few months.
3 months. Okay, because that's a very interesting project. Thank you very much.
Thank you.
Who is next? Can you come this way, please?
Can
you keep your questions short, because actually we're running out of time.
Yeah, interesting topic. So my question is, the Huohua library is in future, is that library for not only processing tool and also like all the analysis tool for time series?
Yes. So the basic the goal is not just for manipulating data, and also provide all the analytic functions to analyze the time series data set, like the linear regression model or like the t-stats. We want to provide all kinds of commonly used, similar to pandas, Python pandas functionality to Huohua. That's the goal.
Okay, we have one last two questions.
Are there any plans to, because it's very useful for frequency domain analysis, if you want to move into the frequency domain. So are there any plans to provide some functionality for that? Like for example, if you want to capture a sequence of events rather than just one event. So right now you're taking one row as one timestamp, right? So if you want to capture a sequence event, you would move into frequency domain. So how would you, I mean, are there any functionalities, plans to do that? I see a lot of applications there.
So sorry.
When you move into frequency domain, suppose you want to apply digital signal processing techniques on this, right? So
I'm not quite sure. Not quite understand your question.
No problem.
Could you?
One more last question.
Thanks. So the first was, in your temporal joins, have you found that the sort of look back to the last value is sufficient for most of the problems, or are you planning on implementing some sort of like interpolation between values to maybe get a better join instead of just increasing the window?
So you mean people when people do this kind of join, how do they choose the parameters for the window size?
No, I mean, like, is it always the best to look back to the latest value because it may be stale, or maybe I want to do this temporal join but I need a data point there. Is it better to have nothing or interpolate, for example?
So yeah, it's always like it's better to like you have infinity windows. Then you basically then you find like whatever the latest value from the right hand side I can match. That's I mean ideally we should do that, but that will basically significantly slow down the system first. And most of the time you have knowledge like you know the data at least will present like once a day, one or twice a day. So you know the window size not necessary to be that long.
Okay.
That makes sense?
I think so, but when you have data of different resolutions, you just look back seems to be sufficient for most analysis.
Yeah.
Okay.
All right, thanks a lot, Menbo. Give a big hand to him.